problems that I feel like that'll test a lot of concepts, and we're going to go through each one, as in like I think there's like 14, 15 like chapters I guess in ACS. So I selected a few out of those. There should be like a total of 50 something, and then after that we should have time left over. So feel free to come up, ask me like any questions, anything like that. Feel free to talk to me when I'm up here too, or if you can't hear me, tell me that. Does that sound good with everyone? How are y'all doing today? Good? I mean, better than nothing, I guess. All right, so we're gonna start with the classic nomenclature. This is like a pretty easy place to earn points, and it's a pretty easy place to like lose points. But as long as you know the few simple rules in general, it's not bad. Can everyone hear me? Kind of? I'll get the mic on. All right. Hey. All right, can you hear me now? Sweet, okay. I guess I'll stick with this then. And then everyone else in the back gets a free Orgo 2 SI review, even though they're probably not in it. All right, so we're gonna start with NM3 from your ACS. And it's just like one of those, what is the IUPAC name of the compound? And I'm going to draw the compound for you guys. And two. So what's the main thing to know when we're dealing with prefixes and suffixes and deciding which one's going to be our suffix and which one's going to be decided as a substituent? So like in this case, what I'm saying, we have an alcohol and we have, I'm like moving it on my computer screen. I keep forgetting you guys actually can't see it. All right, so that being said, we have an aldehyde and an alcohol, right? And we're kind of trying to decide, will our name end in OL or will it end in ONE? So how do we just decide between that? Does anyone want to yell it out? And feel free if you guys are kind of shy. When you're deciding between these, it's actually just a generic list. There's not like something that, like a trend or a concept. So it's kind of like you're deciding priority. And in this case, ketones have priority over alcohol when naming. Does that make sense with everyone? Okay, and then so that means our ending should be the one that has priority. In that case, it would be NONE. So if I were to make like a list of like, for naming, the things I should do, I guess the first thing to do would be one. Can you guys? Yeah, feel free to tell me if you can't see anything. So I'm going to make a generic list on how to approach naming. So first thing to do is number the parent chain. So in this case, what is our longest parent chain? Sorry? 7, right? So then what would be would it be hexa or hepta? Hepta, right? So that's going to be our longest one, and it's going to be 1, 2, 3, 4, 5, 6, 7. And then we said that the ketone will have priority, so that's going to end with NONE, right? The other one's kind of like a list of things that have priority in general. So a little side note, when naming, if we were ranking them, so it's going to be starting from carboxylic acid, in ester. I probably should have continued that trend, but I guess I'm mixing it up. Acid chlorides. So if you guys looked up just basically on Google a list of what takes priority when naming, this list will come up. So that's kind of saying if I have two substituents, which one will actually be at the suffix or basically be at the end. Does that make sense? Is that kind of good with everyone? All right, so for this one we said it's going to be hepta, and should we start from this side or this side? What do you guys think? This one, right? Good. So we're trying to start with a place that will have the lowest set of numbers. So which Do you guys have your ACS out with you? What do you guys think the answer is? I guess we'll go off of that. Sorry? Hey, good. Does everyone agree with that? Kind of. So A would be 4-hydroxy. Methyl 2-heptanone. So if I was going to continue my list on what to do with nomenclature, the second thing would be to look at the substituents. So it would be name and identify substituents. And then the third thing, you would number the parent chain, which you guys did perfectly. And the fourth thing, just kind of a general list. Arrange substituents alphabetically. Well, I guess I can't spell. And then the fifth one, which is going to be over here, just look for any type of stereochemistry and put that in there. Does that make sense for a general list? Can you guys see that? All right, cool. All right, so the next one we're going to look at is, I guess, number 3. So just number 3 on this chapter of nomenclature on the ACS. We're going to go hit that one. So do you guys have that up right now? Is that cool? All right, so kind of looking at your ACS because I can't throw it up on there. The compound that we're dealing with, so we're going to do number 3, is E, 1, 2, dichloro, 2-pentene. Bless you. All right, so when we're dealing with E and Z, that's kind of like a stereochemistry thing, and that tells us whether what. So like if I had, we'll do just a generic example. Say my R group was here in an H, and then my R group was here in an H. Would this one be E, Z? Like what do you guys? Z? Good. So we're going to go with Z. Does everyone agree or disagree with that? Go with E2? So yeah, the way I remember it, so in this case it would be E. So you're kind of comparing these two. The way I remember it is kind of dumb. I kind of think of it as like same Z, which makes no sense, but it sits well with me. So like when I'm saying same, it's like the R and the R group, they would be on the same side, so that would be Z, so they're larger substituents. Does that make sense with everyone? So in this case, it would be E, so they should be on opposite sides. Is that kind of so well? All right. So with that, so we know that so far. So just looking at our answer choices, we can pretty much eliminate which ones between A through D. Yeah, good. So we can eliminate, which one did you say? A and B? D, thank you, sorry. Can't really hear up here. Okay, good. And then when we're naming the rest of them, how do we determine which has priority for these ones? So, sorry? Yeah, good. So we're going by weight, and we eliminated this one, and we eliminated, is this going to be E or Z for A? This one would be Z? Okay, good. I guess I marked that one off. For some reason I marked A as in that. Not sure weird. In a second. Because this should be if we're doing priority for E, this would be on opposite substituents, right? Yeah, that doesn't, yeah, that was like, I was looking at it, I was like, wait, that doesn't, yeah, so which one would actually be B, right? Okay, good. Yes, so the ACS is wrong, so that's a good start. Good call with that one. So does that kind of make sense for determining E and Z? And then pentene with the E and E gives us like obviously a double bond. The question?
Why is A wrong? I thought chlorine has a higher atomic number than carbon. And then don't you compare them by which two they're on each carbon?
For the chlorine and
Yeah, orange is like on each carbon. So if you're on the left carbon of the double bond,
yeah.
comparing the CH3, CH2 to the hydrogen.
Mm-hmm.
Obviously the CH3, CH2.
Yeah, they're on opposite. Yes.
On the right one, and you compare the CH2Cl to the Cl.
Yes.
So then that would be
So 3 is not. Now we're back. 3 is not actually wrong. So 3 is E. Good. So we're going by weight and
CH2Cl weighs more than just Cl.
you go by directly attached, right? Does that make sense? So yeah, so you go by what's directly attached, like the first one. So like she said, the Cl and the CH2. So for A, your Cl would get priority, and on the opposite side, the CH2, CH3 would get priority. Does that make sense? Okay, so we'll try that again. In this case, you look directly at the substituent that is attached to it. Cl, and we're going to do this case, CH2, Cl, and H. So we're looking at the one that's directly attached when comparing these two, right? Disagree, agree? Kind of. What do you guys think? Is this right? Yes, no? Maybe?
When I was studying, I saw it shows if it has a whole chain, that's bigger than just a metal or something, you go with the chain.
Really, so even though this one would be weighing more, it would go with.
Cl still attached to the CH2, yeah, still part of the same chain.
Okay, so definitely check that back with, because we're getting a little, what's up?
So you're saying that's A, right?
Yes, this one's A.
Would B be the answer because it's E, meaning the R groups are on opposite sides, and that one, the R groups are on the same side?
So R group in general, it's like, I should have put something else for R group, which is just carbons in general. It's kind of which substituent weighs more at that point. So right now, we're a little conflicted on, is it dependent on just the first molecule, or is it dependent on the whole thing? So we're going with the whole thing? So we're going with the first one? So do you guys want to get a back reference on defining it?
It's based on the Carbonyl relog, so it's the exact same way that you determine RNS.
Mhm.
Only go to the whole chain if it's the same. Like if that was carbon versus just like if it was CH2Cl versus just CH, like a tiebreaker. Yeah, if it's tiebreaker, then you go down the chain.
Good.
Look at the one that's immediately connected.
Mm-hmm. Good. So does that make sense with what she said? Okay, so kind of like with RNS, you're going down to, wow, that's really loud. You're going down each one. So you look at the first one. If these two had both carbons and then a CH2Cl, then you look at the next one and the next one and the next one. Do you guys want to do another example like this? No. I got a guy in the back just like, nah, I'm done with this stuff. E and Z is just too much. Yeah, let's look at 7, which is right next to it, and determine whether E or Z is going to be our right one. So what do you guys think about 7? Is it going to be? It's going to be Z. Good. That one's a little easier than the one that we just did. But going back to what she said, should be the one that's directly you look at the first one, and then if these were the same, then you look at the next one when determining an E and Z. Does that make sense? Kind of like with R and S when determining priority. It's like really similar. What's up?
I didn't understand that, but I thought E and Z were based on our group. I thought ours were carbon chains.
E and Z in general
Yeah,
were based on R groups?
yeah, like the carbon chain for B is on the bottom, so that would make it. Can CL be an R group? Is that?
It would be an R group. It's kind of like she said, priority with R and S.
But
So like I put R groups in this example. It doesn't have to be R groups unless I've read the textbook completely wrong. If you like, honestly, go and back check with me and see if that just, and then you can just make sure to everybody, because I obviously don't want you to go with the wrong information, right? I was kind of just going off ACS for most of this stuff. So this one we will come back to. So number 3 we're going to come back to. Let's do number 7, and we said this one was Z, right? That kind of makes sense to everyone? Okay, and then after we do that, we count which way? Do we count from, if we're looking at number 7, do we count our largest parent chain, which is how many carbons? 7, right? And do we start from the side that the OH is not on, or do we start from the opposite side? Good, yeah, so we start with the one from the OH, and then we'll name that from 1, 2, 3, 4, 5, 6, 7, and my double bond will be on the 4th carbon. Does that make sense? And will be ENE. So we're starting with the OH because that has the highest priority, and when we're starting there, we can have the lowest set of numbers when naming it. Does that kind of make sense with everyone? So naming, just like knowing the few rules and how to approach that. All right, so the next one I have up is 8. Do you guys know the difference between phenol and benzene when naming as substituents? Yeah. Good. So we're gonna that's the thing that sometimes it's forgotten. So which one is the one that has phenol, or like what's the difference between the two when naming a phenol versus a benzene? And on the benzene? So if benzene is going to be our substituent, it should have a CH2 and then the whole ring system. So in this case, is that what we're looking for? Not really, right? So we're looking for phenol. So which one does not have that CH2 directly attached to a benzene ring? Because if we're looking at A, is that a benzene or a phenol attached to the amide? So on the right side of the ring, it's a CH2 and benzene. Well, I just gave the answer away. Well, yes, that's benzene, because that's the CH2, and we're naming it as our substituent. If we go to B, the same exact thing is there, and it's going to be CH2 and the benzene, so that would still be benzene and not phenol. Does that make sense? And then C is the one that also actually doesn't have benzene, so that actually is a phenol group. Does that make sense? Because it doesn't have a CH2 and then a benzene. Is that cool? So that's why in this case we're looking for phenol, and C would be our best one because there's also nitro on the benzene ring. Because if we're talking about 4N-phenyl 4-nitrobenzamide, which one should have the nitro group? Which do you guys think should have? Between C and D, which one would have the nitro group? The benzamide or the phenol group? Going off the name. It would be the benzene group. So the one attached to amide should have the nitro group. So in this case, it would be C. Does that kind of sit well? With everyone, does that kind of make sense ACS-wise or not? All right, sweet. We got like a thumbs up in there. So we're gonna do number 10, which is just like, what is the IUPAC name of this compound? So another classic IUPAC question. So let's start with how long is the parent chain? So if we had our rules, so what's our longest parent chain in this case? For number 10. I'm gonna draw that really quick. No, that's not an aromatic ring. So what is our parent chain going to be in this case?
Are you going based off the printout or like?
I was actually going off the ACS in general.
Oh, okay.
Yeah, so do you guys have number 10 ACS? Do you guys have access to ACS? So this was just number 10 on the ACS. Are you guys, do we have the same question? That's not supposed to be an aromatic.
Can't see it.
Oh, thank you. So this one, number 10. Do you guys see this for number 10?
Yeah.
Okay, so that's the one we're naming right now. And what's going to be our parent chain? So what's going to be our base naming part? Good, so cyclohexene, because there's a double bond, ignore whatever that is. So we're going to have a cyclohexene at some point. Hexene. And we'd probably have to tell where that is going to happen. And this is, but when we're doing priority of substituents, what takes priority when we're dealing with this? Is it the ketone or is it the double bond alkene? Double bond will take priority when naming, so it would end with ene and not one. Do you guys agree or disagree? Yeah, so ketone in this case would take priority. So it's going to end with one. There's like a generic chart of what takes priority. So this is an example of that. So it's going to end with one. Good. So it's going to be cyclohexanone. And then we can start from pretty much there. And so then we know the ene part is going to be not the N because it's not the one that's starting with the substituent. So how should we name, or like how should we identify it's going to be ENE? Or like how should we start a numbering? Should we start from 1, 2, 3, 4, or should we go 1, 2, 3, 4? Should we start from the double bond? So our double bond would be 2 on the second substituent. Okay, so then it would be 2 cyclohexanone. So it would be like that. Do we see a 2 cyclohexanone on ours? Okay, and for multiple choice, do we have to actually go through the rest of them if we see that part? No, so like the ACS, they could get confusing, but like at the same time it is multiple choice. And ACS multiple choice is, in my opinion, I think easier than the one she has in her test. Which I'm probably getting some weird faces from that, but it's understandable. They just have like a weirder language, in my opinion. I think hers is actually maybe more difficult. So in this case, we don't actually have to look at the rest of them because we got the 2 cyclohexanone, and we'd want to start with the one that has the most substituents, like you said. Does that make sense with number 10? All right, so we're going to go to number 11. And this is kind of like, have you looked at your functional groups in general? If you guys could look at number 11. So which one has basically all of those functional groups? Or what does an amide look like in general? If we're doing 11, how many of you guys think it's A, has an amide, a ketone, ester, and ether? So if we were doing functional groups, An amide would be NH2, ketone, ester, and what else are we looking for? Oh, that's an ether. I'm dumb. Ether and ester. So we're looking for something that has all of those, and basically which one has every single one of these. Be good. And NH2 group is just a what group? An amine group. Good. If anyone actually said that, or maybe I'm hearing things. So yeah, so A is definitely not it. And in this case, number 10 would be B. Or 11, sorry. 11 would be B. Now we're going to head on to structure and hybridization and all of that. Does that sound good? So this is the next kind of chapter. We're going to start with St1. Does that sound good? Do you guys have that up when it's just asking what's the acceptable Lewis structure of carbon monoxide? Is that cool? So what's the first thing we should do when looking at this? So we're doing St1, and we're trying to get what's the Lewis structure for carbon monoxide. So the only two questions you pretty much have to ask for all those answer choices is, one, does it account for all the valence electrons? So we should have a total of how many valence electrons? So how many valence electrons does carbon have in general? 4. Good, 8, 4. So yeah, 4 valence electrons, octet rule. Good, you're getting ahead of me, but yeah. So carbon has 4 valence electrons, and how much does oxygen have? 6, right? And 4 plus 6 is? Nice. So yeah, so 4 plus 6 is 10, so our structures should have 10 total. So the first thing I would do is count valence electrons. And if I was looking at my question, let's see which ones don't have 10. We can just start by that, just eliminate. So does A have 10 valence electrons total? So that's good. And what about B? A total of 10 valence electrons for B? Okay, so B has it. What about C? No, that has like 14. And D, what about that one? D, 4, 6, 8, 10. Nope, so we can eliminate C and D, and then what's the other thing we should look for, which is the second rule? Good, octet rule. So we kind of have to see if they all satisfy the octet rule. So let's start with A, which is just a C double bond to an O, or triple bond, sorry. And for the octet rule, all you pretty much have to do is check if it has like 8 basically electrons for filling it in a way, which is probably the worst wording that I could have come up with. So in this case, you have 2, 4, 6, 8, because there's 2 electrons per double bond. So does this one fulfill the octet rule for carbon? And what about oxygen? Yeah, right? And then what about B? Does that fulfill it for carbon? Not for B, right? So in this case, our answer would be A. Is everyone? Thank you. So yeah, our answer in this case is A. So that's just the things we should do when seeing if it has a Lewis structure. That's correct. So the next one that I have that we were going to do is number 3 in this. Yeah, what's up?
Can we start on like harder things? Like I feel like we have, I don't know, but like I feel like this is like a lot of review that we've already been going on.
Okay.
We have an hour left.
Okay, yeah, we can definitely do that. Do you want to, how do you guys feel about that?
Yes.
Would you want to start towards, is there a specific chapter or section you guys like to start with?
Like
The reactions from Orgo 1 or Orgo 2? Orgo 2? Okay, so what I'm going to do is speed through this because I still have to follow like a set thing, and we'll get through this a little bit faster if everyone's doing, if everyone gets this complete, then we'll just go through this pretty fast. Is that okay? Because we still kind of got to follow the, so we'll do, I'm guessing we're good with 3 after doing that one? All right, and then what about 4? Does that one make sense? Feel free to say if you're not feeling good about this. Yeah, ST5? You want to go do? So let's do one at a time with this one, and then after we'll select other ones. So how do you guys feel about 4? We're good with? Yes, no, maybe? Okay. And then let's go to 14. How about this one, classifying aromatic structures? Do you guys want to do this one? You don't want to do it? Too easy? All right, what do you guys think for 14? Everyone's good with classifying aromatic structures? Dang. So what's the answer, just really quick? Is it A, B, or C, or D? It's A? Okay, so 14, we're going to go with A. Is 1 aromatic? Does it fulfill both of our rules? Does it fulfill Huckel's rule? 4n plus 2. So we have 4 pi electrons in this one. How do I get 4n plus 2 is equal to 4? So what should n be if I was trying to get this to 4? Yeah, so this one, the first one doesn't fulfill Huckel's rule. Yeah, so it has 2 double bonds. So how many pi electrons would 1 have? 4 or 6? Does the cation have electrons there? No, right? We're looking at 14, right? Yeah, there's only 4 pi electrons in 14's case. Does that make sense? So actually, if it doesn't fulfill Huckel's rule, which is the second one, but fulfills the first one, which is conjugated p orbital, if it doesn't fulfill this one, but fulfills this one, it's going to be anti-aromatic. So the first one wouldn't be aromatic. Do you guys kind of see that? Why the first one's not aromatic? We're all good with that? Okay, so we'll go to the next one. You guys also good with 15? Really quick, what did you guys get for 15? A? Good, so does that make sense? This boron doesn't have a lone pair, so it's not going to be 6 pi electrons. It's not going to fulfill Huckel's rule. We're good with that? All right, so let's go on to the next chapter, which was acids and bases. And I think I just started at number 2. I think this one would test concepts a little bit better. Look at AB6. This is kind of tying in deactivators and activators and asking which is the strongest base. So we're going to get AB6 for acids and bases, and is asking which is the strongest base. Do activators make it a stronger base or a weaker base? What do you guys think? So that's what it's kind of testing. Do activators make it stronger or weaker in this case? What do you guys think? So we're between do activators and deactivators. And we're trying to determine which one will be the stronger base. So when we're talking about electrons in general, would I want my electrons to be delocalized or localized for the base to be stronger? Localized or delocalized? What do you guys say? So, or does that not make sense? Okay, so let me draw this really quick. So this is our question. We'll just start with NH2. Not a double bond. and you have a lone pair right here, right? And if I was trying to be a base, and a base is like also sometimes a nucleophile, it needs these electrons to go and attack, right? Does that make sense? So I would want my electrons to be staying there if I want to attack stuff. Does that make sense? So then I would want my electrons to be localized for a base. So bases, electrons should be localized. Does that make sense? If I have a activating, or let's say I have a deactivating group, is it going to pull my electrons when there's resonance going around? Right, so deactivators take away electron density, so say if I had resonance, sometimes my double bond will come out here and the deactivator would take it away, right? A way to look at this, if we want our, basically, and all of these they have resonance, right, because of the aromatic ring, so it's asking which one has basically less resonance in a way. Which one are the electrons more localized? So in the case of NO2, if it's going around the ring and then it has to also go through NO2 and come back around to become the lone pair again, that takes a little more time, right? So if you think about it, like if you were in a house, an NO2 group is basically an extra room, and now your electrons, say like this lone pair, has an extra place to go out of the ring. Does that kind of make sense? But if it was like an activator, these electrons, this resonance, it wouldn't go out of the ring, it would go into the ring. So it doesn't have that extra room. Does that kind of make little to no sense? Or? So if it was like going around a circle, it just has a larger circle to go around because the NO2 is also withdrawing electrons. So my electrons won't be there most of the time because they'll have trouble going through all this stuff. So it's going to take longer to come back. Does that kind of make sense? Or no?
Why is NO2 a room?
So NO2 is going to withdraw electrons, right?
Why?
Because it's a deactivator or activator.
I don't know what you guys mean.
Sorry?
I don't know what you guys mean.
So in chapter 22 with aromatics, we deal with activators and deactivators, right? And when we're talking about activators, they add. So let's just do a generic activator. So OCH3. So this one has electrons, and it'll donate to the ring and help resonance take place. There's more electron density in the ring, so reactions would take place faster. Does that make sense? With deactivators, so like NO2, so this is a really good question. So with NO2, for example, this one is very electronegative, so it'll pull a ton of electron density out of the ring, and the resonance would sometimes go out of the ring and do resonance with NO2, unlike this one where this adds electron density into the ring.
So isn't the electronegativity that overcharges an activator, deactivator?
Yeah, it's somewhat electronegativity, its ability to pull away charge. In this case, NO2 pulls away a decent amount of charge. And then it's kind of like, if I want my lone pair to stay on my NH2, and now I suddenly just added another extra set of resonance that's pulling it away, my lone pair is not going to be there as much. Does that make sense? So it's not going to be as localized. So I'd want an activator or deactivator to be the strongest base. Right? So good. Yeah, I'd want an activator. And in this case, if we're looking at AB6, which one has our strongest activator? A, B, C, or D? B? You guys good? B? Okay. So let's go on to the next one. Good question, by the way. So acids, bases. Let's go to number, I think 2 is a review of something very similar we just did. What did you guys get for 2? Just looking at it quickly. For number 2 on acids and bases, what are you guys feeling for that one? So we know that deactivators make it less basic, right? And NO2 are deactivators, so I don't want those on if I want it to be stronger. So it's not going to be C or D, right? So what about A and B? So why do you say B? Are the electrons participating in resonance? So yeah, good question. So number 2, we'll just look at that. Let's just do a generic example. This one, just say there was a double bond here, and then in this case, we'll just say there's not. If my lone pair has to act as a nucleophile in a way, act as a base, it'll have to go and attack stuff, right? Does that make sense? But if it can participate in resonance, it's not going to be there all the time, right? So it's not going to be localized, right? So this one, so in case A, those electrons won't participate in resonance, so those electrons are going to be more localized. Does that make sense with everyone? So if my electrons are staying where they are, they're not going to participate in resonance, then they have more ability to act as a base because the electrons are going to be there. Is that good? Okay, so number 2, and then we'll do number, I think you guys agree with number 3. How do you guys feel about number 4? Yes, no, kind of like the classic conceptual acid-based questions. What do you guys get for number 4? Anything? Was this one kind of easy, kind of hard? So we're going with A for number 4. Do you guys want to do this one? All right, so let's go one at a time then with this one. Let's compare 1 and 2. So which in order from the strongest acid, weakest acid. Normally, things with negative charges, are they bases or acids? Bases, right? So my positive charges are probably going to be pretty acidic compared to the one that doesn't have a positive charge. So between 2 and 1, which one's more acidic? 2, right? And between 3 and 4, which one's more acidic? 4, right? So we know that 2 and 4 are definitely going to be our more acidic ones, right? And if we're kind of looking with OH2 and NH3, which one between O and oxygen and nitrogen, which one's more electronegative? Oxygen, right? And if we just had let's get a different sheet of paper, and and another way to think of this, between O, let's say, and this H, and this N, and this H, if this one's more electronegative, would this double bond, would this bond right here be like weaker or stronger? Stronger? Would they be sharing as much? Not really. So most of the electron density would be closer to O, right? What about nitrogen? It's still pretty electronegative, but which one's more electronegative? Oxygen, right? So most of its electron density is going to be around the O. So this bond will actually be a little bit weaker. Does that make sense? So if it has a weaker bond between the H, it's more easily donates hydrogens. Does that make sense? And the more hydrogens I donate, the more acidic I am in solution. So going by number 4, that should be between this one, it should be 2, 4, 1, 3. Does that kind of sit well? So that would be, I think, A in this case. Yeah, we all good with this one? Maybe. All right, so let's do number, how do you guys feel about the acid stuff? All right. I had number 8 down, but if we're good with it, we can skip it. So how do you guys feel about number 8? What do you guys get for acids and bases? Which one would have, basically, which one's the most acidic proton in this? The smallest pKa value. So is it going to be D? So why do you say D? Yeah, so the triple bond, this one is very acidic compared to the other ones, which is one's a double bond, one's a single bond, one's an aromatic ring. An aromatic ring is not going to donate a proton because then it's not aromatic, which is very stable, so why would it do that? The triple bond, this bond is like very, very small, so it will actually, well, very short, so it's more able to donate this proton because a carbanion is actually more stable than a alkene. So we're kind of like, the ones that will donate a proton are the ones that are decently stable after they donate it. Just kind of thinking about a triple bond versus a double bond. A triple bond is generally just more stable in general. Does that make sense? So yeah, D would be this one for 8. Let's go to stereoisomers. You guys feeling all right about acids and bases? Thanks. All right, so stereoisomers. Let's go through just the quick configuration for this one. We'll just do number 1 for stereoisomers, which is an R configuration, basically. For number 1, what's the, or should we do this one really quick? I'll put up one of them. COH, CH3, H, and this one. So when we're dealing, which one has number 1 priority for this one? This one, right? Oxygen would have priority. Then what's next? Good. And then what's the third one? 3 and then 4. So what is my configuration in this case? So 1, 2, 3, S. So yeah, this one's S. Good. So we're looking for R, and that's not it. What about B? Not too much B. What about C? How do you guys feel about C? Yep, so yeah, that one's, we're all good on stereoisomers and this stuff. R and S is pretty easy. Okay, so yeah, 1 would be C. So let's go to number 5. Which one of these are meso isomers? So what do you guys think? Which one of these are actually meso? 1, 2, and 3. 1, 2. What are you guys feeling for number 5? Or what are meso compounds? So in this case, I think the easiest way to tell if they are meso is if there is a line of symmetry and they're in the same plane. So all you have to check pretty much is if there's a line of symmetry and these two are in the same plane, as in they're both wedges, that's going to be a meso compound. Does that make sense? So it's just like the quickest way. So you would have to have 2 separate, supposedly chiral parts. Does one have that? Choice 1 in number 5? Are they on the same or different in choice 1? The same, right? So is that going to be a meso? Is like choice 1 even chiral? Not really. Doesn't have 4 different substituents, so we can throw choice 1 out. What about choice B? Is there symmetry, and are they on the same? Yep. So yeah. So choice B would be meso, and then there's no other. There's not a 2, 3 option, so we can go with 5 being B. All right. So let's do. Go on. What's up? Number 4. Which compound will have 3 peaks of equal height? So we're going to go through just these questions list really quick, and then we'll hit these next ones. Like after, we can do extra questions, okay? So after 5, I had 8 down. How are you guys feeling about 8? Yes, no? What are you guys, constitutional isomers, or are they enantiomers? So the easiest way, I think she said this in class, is just to see if they flip, everything flips in the plane, right? So in this case, does everything basically flip in the plane? Like, does the OH just go to the opposite side? And does the CH3 also go to the opposite side? So what would they be? C, right? So they'd be enantiomers. So let's do What about number 9? Would this be a racemic mixture? Would this be a... So this is kind of a test of Orgo-1 reagents. What do you guys think? Is it going to flip the configuration, or is it going to make it racemic? Good, yeah, so this one's going to make it racemic, especially because a carbocation will form. So number 9, just a quick one. When you have your carbocations in general are just planar, so your bromine can attack from either side. So in this case, it's going to be a racemic mixture. Does that sit well with everyone for number 9? Okay, so yeah, that's an Orgo-1 reagent. So let's go hit number... I think we did number 12 in class. How do you guys feel about number 12? We're all good? What's up? Number 9 was, we said D for racemic. Does that sit with everyone? We're all good with that? Okay. So then let's go to number 12. I think we did this in class. What do you guys think about number 12? Enantiomers? Yeah, good. So just make sure you flip it the right way, because they just wrote one upside down. They just tried to trick it. That's one's pretty decent. The next one I had was 25. Which one would yield a meso product? So this is just a review of reagents. So which one is going to add syn or anti addition? D. So D is going to add syn addition. We're all going to agree with that for number 25? Yeah, maybe. What does H2O and H plus do to the double bond? What does it add? Good, so that one adds an OH, and that's just one OH. That's not going to help. Same with HCl. And what about Br2CCl4? Is that going to be anti or syn addition? Anti, good. So yeah, that's not going to be our meso product. So yeah, good. D is going to be our answer in that case. So let's go to the 5th chapter with nucleophilic substitutions and elimination. I have question number... Question number 2 down. How are you guys feeling about question number 2 for nucleophilic substitutions and eliminations? Do you guys get this one? You guys want to do number 2? What do you guys think the answer is between these? So if we're looking at number 2, it's saying, this is number 2, and it's saying that we're treating 2-bromide, okay. Well, I picked a long, fun one. So it has potassium hydroxide, and what's the other base that they use? It is potassium tert butoxide, so KOT. So what's the difference between, or KOET, what's the difference between potassium oxide and potassium tert butoxide? Which one's more bulkier, I guess? Right, good. So which one, and that's producing 70% of that kind of product. Does this question make sense to you guys? So if we're looking at that question and we're going with, it's saying KOH is producing 45% of 2-methyl-1-butene, all right? So they're both producing the same exact. So they're both producing 2-methyl-1-butene. This one, KOET, is just producing a lot more of it. And that's not the same. So they're saying this bulkier base is producing a lot more of this. Does that make sense? While this base that's not bulky at all is producing only 45%, right? And then what about potassium protoxide? So that's just this KO, and then 1, 2, 3. So is this more bulkier than KOH? Is it more bulkier than this one? No, right? So do you think it'd produce more than these guys or in between? Yeah, so it'd be in between, which is kind of just asking you a long way between 45% and 75% or 70%. Does that make sense? They're just kind of trying to bog you down with words. So let's do number, what do I have? How do you guys feel about number 7? So will there be multiple products? Will there not be multiple products in 7? There'll be multiple products. Good. So, and then what will our products basically be for 7? Which ones do you guys get? B? Okay, good. So I think we're pretty much are okay with 7, just a classic elimination reaction. Okay, so then let's go on to, what do we got next? I think put 8 up. What do you guys get for 8? How are you guys feeling about 8? What would be the major product of dehydration of 2-chlorpentane by potassium oxide? Would it be, I guess I'll draw this one out. So it's basically asking where my double bond is going to go, right? And where will the double bond, in this case, where do you guys think it'll go? Will it go to the less substituted or more substituted? More substituted, right? Yeah, so that makes sense. Yeah, so it's pretty much going to go at the more substituted position after it gets eliminated. We're all good with that? So the answer, oh, I can't see it? Oh, my bad. So the answer in this case would be, it's going to be eliminated to the more substituted one, so it's going to be B for number 8. Does that make sense? There won't be any rearrangement, especially in elimination. We went to 27. How do you guys feel about 27? On this one. So it's kind of like we're between a, which one reaction would produce? Wait, am I looking at the wrong one? I'm looking at 20. Oh, sorry, I put the wrong one. So 20, 22. Oh, sorry, 22. So for 22, is this an Sn1 or Sn2? Or how do we tell for this case? So to determine, let's leave 22. So just to determine between Sn1 and Sn2, the first thing to pretty much do is look at what? Where should we start? Yeah, we should first look at the reagent. Is it strong or weak? So in this case, is NaCN a pretty strong base? Yeah, it's a really strong base, so it's either going to be Sn2 or E2. So we're between those two right now. And in this case, do we have a good leaving group anywhere? Is kind of what we're looking at next for Sn2 and E2. We don't deal with OTS too much, but that's actually a pretty good leaving group. The ACS likes to deal with it, but that kind of tells us that it's going to be a substitution reaction because there's a good leaving group there. Does that kind of make sense with everyone? So does Sn2 make it a race mixture or does it inverse stereochemistry? Inverse, right? So yeah, all Sn2 does is inverse stereochemistry. So yeah, the first thing to do is look at the reagent and then decide from there what to look at would be the substrate. So in this case, it's going to be R, right? It's going to flip configuration. We're all good with that. So 22 would be B. All right, so let's go to, how do you guys feel about 30? Predicting the major product between the cyclic structure. For number 30, we're all good? What do you guys get for that? C? For 30? Yeah, we can do 30. So 30, you have this structure. And you have CH3. If you're dealing with a strong acid in any, pretty much most, so if you're stuck on your test and you're like, I have no idea what's going on, if you're dealing with a strong acid and you can identify this is a strong acid, you know the first thing that's probably going to happen is it's going to donate a proton, because that's what acids do in general. So it's probably going to donate a proton to here. This has an electron. This will take a proton off. And you'll have this OH group, and that will, is this a substitution reaction or what is this? What do you guys think is going on here? Is our, if you kind of look at our choices that we have, is the OH still there in any of our answer choices? No, right? And what's there instead? A bromine, right? So that's going to be a substitution reaction. So we're trying to figure out what is going to happen. And when we're talking about rings, what's a more stable ring? 4-ring or 5-ring structure? 5-ring structure, right? So that's just more stable in general. So this OH group, once it, so I'll draw that. CH3, CH, and then is water a good leaving group? Yeah, right, so that's gonna leave. Can you guys see this? Okay, yeah, so once that leaves, what's this gonna be, positive or negative? It's gonna be positive, right? And let me just put that out and I'll show you kind of what it looks like. So let's leave it CH3 and then CH. This is gonna be positive. And then we have a CH3 here. So in this case, what's going to happen, because a 4-ring structure is not stable at all, it's going to try to switch to a 5-ring if it can. So in this case, this carbon is quite positive. So this bond right here is going to open up and make a connection with it right there. So this bond will break because 4-ring structures are just very unstable. And then if you were to draw this part instead, that would look like you would have this, and then you would have your CH. Between C and D, what did you guys get? So you have your CH3. And then you'd have your positive, and then your other CH3. And then where would the bromine go attack? Pretty much at the positive, right? So yeah, so that would just be Br, CH3, and CH3. Does that kind of make sense? Why it goes to a 5-ring structure? So yeah, it's going to try and open up and break to adjust to a 5-ring. Are we all good with that? So this 30 is a little bit weird to visualize. So let's go to electrophilic additions, which would be the next chapter. So let's look at number 2. So this is just a review of the reagent. Does this reagent add, is it going to add Sn? What is it going to do in this case? Electrophilic. Is it going to add the OH on the more substituted or less substituted position? less substituted, right? So this is a review of hydroboration oxidation for BA. So BH3 THF and H2O2 and OH. So that adds an OH to the less substituted. Less substituted. So I would suggest, like, when you're going through the reagents, the things that you should know is where it adds it, or like basically what it's adding, what is its regioselectivity, so is it going to add more substituted or less substituted, and then stereochemistry. And if you can pretty much know those for the reagent, that's not like too bad. I think you'll have like a decent chance on the test, because that's pretty much most of synthesis. Let's do number 7. So which one adds an OH on the less substituted, basically, which is kind of a review on this one. Oh wait, yeah, that's the same one. I think I wrote a different one down. 3. How do you guys feel about number 3? It's another review of electrophilic additions. What do you guys get for 3? So basically, which one will add an OH onto the more substituted position? D, right? And why can't we use A in this case? Sorry? For H2O plus? Because that also places an OH, but why is that not the right answer? So if we use H0 plus, this one's really prone to rearrangement in general, while D, that carbocation won't move around. Does that make sense? Kind of? So that's why if you don't want rearrangement in your molecule, which will happen with A, so if you're kind of looking at A right now, you may have a hydrogen shift and try and shift it to a more stable carbocation. Does that make sense? But with D, you're not going to have that shift at all. Is everyone good with that? So that's why D would be the one to actually go for. So with Diels Alder, how do you guys feel about that? 14. Yes, no, maybe? You guys want to do this example? Nod, yeah, maybe. Want to do 14? We'll look at it. All right, that's good. So it's 14. I think the easiest way to approach this one or the way to visualize it in a way. So just kind of looking at our DNO file, which is the one that's getting attacked, are these positions tran or cis? Trans, right? So our product is going to be in what? Trans or cis? So yeah, so they'll stay the same for trans. A good way to visualize this, in my opinion, is when we're talking about our diene, you just say 1, 2, 3, 4, and you count it, right? And then your product is going to form a double bond at the 2 and 3 position. Does that make sense? And at the 1 and 4 position is where you're actually going to connect to these parts of the carbon. Does that kind of make sense? So this part in the middle, this 2 carbons in the middle is going to go flip up. And that's where that rectangular table type thing looks like in 14A and B. Does that make sense? So that's just a way to visualize it. And if you're trying to like do retro analysis, you can just do the same thing. Count the carbons, and the carbons between the C, between our DNO file, the double bond is going to disappear. So our product should not have that double bond, and our product should also have a double bond between 2 and 3, right? So which one has that? A, right? Good. So yeah, 14 would be A. So that's just a quick way to visualize it. So let's look at, I think at 18 next. How do you guys feel about 18? I think that's like an unfamiliar reagent. What do you guys think about this one? You guys remember this reagent? So for 18, let's look at this. Let's just look at the reagent, CHCl3, and this terp oxide. Terp oxide is a what? It's a strong base, right? If I was kind of stuck on this and I was like looking at it, the reactant doesn't really have protons that I can see would take off, right? But you do have your CHCl3, and the fact that there's no numbers, like it's not one CHCl3 and then two terp oxide, means that they're mixing the solution and they're also reacting with each other. So just like if I was stuck on the test and I was like, I have no idea what's going on, that can give you a clue if there's no numbers in a way. So what the terp oxide will do is going to deprotonate the CHCl3. Does that kind of make some sense? So this will turn into a CL, and this will be negatively charged. And this is kind of forming our reagent in a way, because this terp oxide is going to deprotonate it. Does that make sense? After that, it's going to just eject a chlorine because it does not want to stay negative. Does that kind of so well? And then what's going to basically happen is we're going to finally make our reagent, which would be a C with 2 carbon and Cl and Cl. So that whole process, that reagent is just forming this whatever this is. Does that kind of make sense? So when we have a double bond, so if I were to place it underneath, and we'd have CH3, H, and H. CH3. How many electrons are in one bond? 2, right? So, and this one also has 2 electrons, so if I were to split this bond, it would be 1 and 1, right? Does that kind of make sense? And then it just connects like a triangle and forms a bond with these ones. It's like a weird reaction, and I don't even know if you guys did this in the textbook. Have you guys seen this before? Yeah, I was doing this review and I was like, I have no idea. So that's why I was kind of like, if you know it's a strong base, you know base is going to deprotonate something. So if you were ever stuck, kind of just go back to the basics. This is kind of similar with epoxides though, because this was trans and this is going to stay trans for 18. So it's going to be B in that case. It's just like a weird reagent. I hope she doesn't throw it on the test. So let's finish with that one. And let's go on to nucleophilic addition and carbonyl groups. Does that sound good? So let's look at number . All right, so what about number 6 for basically chapter 7, or nucleophilic addition at the carbonyl group? How are you guys feeling about it? What do you guys get for that one? Yeah, the reagent may seem unfamiliar, but you guys have seen it. Oh, for number 6 for the next chapter, so nucleophilic addition at carbonyl groups. What do you guys think about this one? This is like, once again, you've seen it, but it's just like the ACS language is a little weird. So let's just look at the reagents. And this kind of gives you a clue, because you're starting with a ketone, right? So that gives us one clue. And you see the first part, which is ethylene glycol, which is this structure right here. And there's pretty much only one place where we use something like this type of reagent. Do you guys remember? Does it kind of look familiar? So this is the one that
Does it look more familiar? So what is that TSOH? Is that an acid or a base? What do you guys think? A base? Good. So we're going to say that one's a base. And what about, and TSOH is not familiar, so I'm just going to tell you that's actually an acid. It's like p-nitroaniline, something like that. ACS likes to use it. So it's basically an H plus catalyst. Does this kind of reagent look a little bit more familiar? And if we were to take off water, does this reagent look familiar? Kind of. This is the one that forms an acetal. Do you guys remember that? Acetal group would be like the OR groups from a ketone. Does that kind of ring a bell a little bit? If we're looking at the reagents that they gave us, which is C6H6, which is just like a ring, that's just trying to say that there's no H2O, that your solvent is basically not having water. And then the TSOH is an acid, and that's where the H plus catalyst comes in. So it's the same exact reagents, doing the same thing, they're just using different ones. So do you guys remember what this one does? It's kind of the same thing with the acetal. It's going to add onto both sides, like in this case, where you have, let's say if I just had an OR group, OR, it would be the same reagents, OR, then the H plus catalyst, and then no H2O. So in this case, because it has this little hat part, it's going to add on to the carbonyl. Does that kind of make sense? This is from like chapter, I don't even remember what chapter this is, like 20 or 23, 22? So this is the formation of an acetal. And this ethylene glycol is not really used a lot besides in this situation. Does that make sense? So if you see this, this kind of gives you a hint, even if I didn't know any of the other reagents. The fact that this is there gives me a big hint. What's up?
Okay, so I have a question.
Yes.
If this was the exact same thing, but instead of the ethylene glycol, you had ethanol,
Mm-hmm.
would it be similar to G minus the OH something else in the, you see how we use it, like, it would be the ethylene glycol with the OH, but you cut off the OH part.
And I cut off, so for B, if I cut off the OH part,
If you cut off the OH part, instead of the ethylene glycol, you just had ethanol.
oh, if I just had, yes. So if it's just like an O with an ethyl group attached to it, yeah. So like, exactly, good. So that would form, so an OR, if instead I had, let's say, just an OH group, it's going to add the OHs on both sides, just like that. And like you said, if you put an ethyl group instead of the H's, it's going to do that. And yeah, take off the OH. I see what you're saying. Yeah, good. So that's what that reaction will do. Good. Good question. So let's do, I think at 15 next. Yeah, what's up?
How would you form like a hem acetal here?
Oh, what?
As side, how would you,
Oh, yeah, it's weird. It's,
the OR, OH instead of two ORs?
oh, hemi acetal.
Like, how would you,
So you would have to use a different reagent, and you'd have to start with a different substrate in general. I will show that. I think there's an example that shows that. But yeah, come after and I'll show you that how it does that. Good question, because we deal with that a lot in carbohydrates. For number, what do I put down next? Or 15B. So let's try and fly through these ones. So it's what is the major product of the reaction shown? This is kind of like with azide synthesis, all nitrile stuff. It's kind of a little random, but it's something you have seen before. But also if you haven't, so if we're looking at 15 and we know that we have like a carbonyl group and we have a ton of NH2s, and NH2s usually act as a what?
a base or they usually act as a base, right? And if I was kind of stuck on this one, which would be our most basic lone pair on the nitrogens? So if, would it be the one that's directly attached to the carbonyl group? No, right? Because those electrons can participate in resonance, so they're a little bit less basic. So the NH2 group that's farthest away is the one that's the most basic. Does that make sense? So going back to our delocalized. So that NH2 will attack the most electrophilic point on the next molecule, which would be that carbonyl group. Does that make sense? So if I just had no idea where to start, and I'm kind of realizing that carbonyl group in general is electrophilic, and that nitrogen in general, amine groups are pretty basic, that gives me a clue on what's going to attack what. Does that make sense? So it was just kind of finding out which one's the most basic nitrogen out of those three. But this is also just a reagent that's straight memorization. NF4 is an imine. So for 15, if we're forming an imine with the last nitrogen, which one would it be? It'd be B, right? We're all good with that? Okay, good. So we're going to move on from 15 to 17, and this is just another review of reagents. Which one adds to the beta position, basically? And that is very similar memorization. It's not going to be a Grignard reagent because that's going to attack the carbonyl group, and Grignard reagents are very reactive, so they will attack the carbonyl group. You want something a little bit less reactive, so that is going to be that's going to be D. So it's like lithium dialkyl cupurate or something. So that will attack the beta and not the carbonyl. Does that make sense? Okay, so that's just another, did you memorize your reagent type thing? So let's go on to chapter 8, number 3. So nucleophilic substitution at the carbonyl group, or number 3. It's asking which would be hydrolyzed most slowly with aqueous NaOH. So it's basically asking which one is the least reactive in general, and which one do you guys think is least reactive? For sorry? Number 3 in nucleophilic substitution at the carbonyl group. So this is the next chapter. So if we're doing reactivity, which one do you guys think is the most reactive or least reactive? So this is kind of going back to acid halides and carboxylic acid derivatives. So if we were listing them out in terms of reactivity, it would be the C. Acid halides, and this would go down to the anhydrides. And then from the anhydrides, it would go down to esters. And then last would be amides in reactivity. So in a general sense, if we're doing synthesis, the ones that say which one's the most easiest way to get to this product, or which is the fastest way, ones that usually go through an acid chloride or turn it into an acid chloride and then do something are really efficient because this is very reactive. So your reaction will proceed very fast. So ideally you want to go through and say if I had a carboxylic acid, I'd use SOCl2 and convert it into this acid halide and then convert it into whatever I want to because it's really fast. Does that make sense? So the one that would be hydrolyzed most slowly would be the least reactive one, which is our amide in general. So in that case, it would be A. We're all good with that? Okay, so let's do number 13. So I kind of give you a hint on this one. So the one that reacts the most fast would be the one that turns it into an acid halide, so number 13. So B, C, and D do that. And we want something that does not get rid of that carbonyl group. And like I said before, Grignard reagents are very reactive at carbonyl positions, right? Does that kind of make sense? So if I were to, for number 13, so the first thing I do with SOCl2 is I turned it into an acid halide. and I just want to turn it into a ketone, right? And I want it to stay like that. Does that make sense? And if I use a Grignard reagent though, after it would attach, like say if we use CH3 MgBr, and it attached the CH3 group and turned it into this, the thing is the Grignard reagent is very reactive with ketones also, so it would come back around and attack the ketone and completely destroy your product. So that's why you don't want to use a Grignard reagent again. Does that make sense? So you only want to use something that works with acid halides and not ketones. Does that kind of make sense? So the one that would do that would be B, because that reagent in general is a little bit less stronger than a Grignard reagent. Does that make sense? We're kind of like yes, no, maybe. Just like because with CHM MgBr, it makes the CH3 a little bit too anionic, so it makes it too reactive. But the copper and lithium don't do that as much. So let's go to number 14. Do I have 14 for this one? Yeah, so what do you guys think about 14? If I said the Grignard reagent, what do you guys think will happen here? Is it going to stay as a ring or is it going to break it? What do you guys think for number 14? Because if the Grignard reagent attacks that carbonyl group, how many bonds would be attached to that carbon? It'd be one too many, right? So then it would come back around and break it. Do you guys want me to draw that, or? Sorry? Draw it? Okay, cool. So we're looking at number 14. And they're supposed to know here. And we have this Grignard reagent, so I'm just going to R group for now, just to make it a little bit smaller. Br, and then let's make that. So this R group is very like anionic because of this magnesium and bromine. So this has a lot of charge. It doesn't actually have this on it, but it's going to act as a nucleophile and attack here and then force this up. Does that make sense? A little bit? And then once it does that, you have this like transition complex where it's going to have your O group here, and it's going to have your also your R and GBR group, and then your R group is just going to be attached there. And then this negative oxygen is going to come back down and it's going to eject whatever it's attached to, and this ring will open. It usually doesn't throw off any CH3 or any R groups, and it won't throw off like a hydrogen group. Does that make sense? But it's going to break here with this oxygen, and the ring is just going to open up. And then for the reason for you have H3O plus is because if I kept having this in solution with ketones, it would keep making this a negative charge. So the H plus gives it an H, turns it into an alcohol. So if I were to see this, I would have my ketone that just formed right here. And then if I go from my ketone 1, 2, 3, 4, so 1, 2, 3, 4, that O group would be broken. And then this would be not a good charge, negative. And then you'd also have my R group that just formed onto it. So that'd be CH2, CH3. Does that make sense? I'm kind of looking, it looks somewhat familiar. A little bit. Yes, this is after the ring is broken, and then it's going to basically attack again because a Grignard reagent is quite strong. Does that kind of make sense? So you're going to have another CH2, CH3 group come in and attack. And it's going to the same exact process will happen. We're kind of seeing it. So it'll go to another one of this, so it's going to force it back up. and then it's going to be you have your CH2, you have your O, you have your, I kind of drew that weird, 1, 2, 3, at this point. So now I have another CH2, CH3 group onto it. Does that kind of make sense? So you should have, by the end of it, you should have 2 CH2, CH3 groups, because the Grignard reagent just keeps doing that if there's a ketone. And then once you add acid, which just has H+, it'll now protonate it. And then you should have your final product. Does that kind of make sense? So I think the only option that gives that is D. Because yeah, once again, the Grignard reagent, if there's a ketone, it'll keep attacking it and keep adding on to it. Does that kind of make sense? So yeah, in this case, it would be D. So let's go to, I think we can, and 15 was just, what's up?
I have just one question.
Yes.
So why is it that when it first attacks, the double bond then comes back down and breaks it apart?
Because in general, a ketone is more stable than an oxygen, that enol type structure. A ketone is much more stable than having that charge. Does that make sense? So it goes right back down with those electrons to get rid of that charge. Does that kind of help?
Right. Would it be the same, like, let's say that oxygen wasn't there in the ring, it was just in the carbon,
Mm-hmm.
would it be the same thing?
That actually would not be the same because those aren't that great at leaving with that oxygen. Yeah, good question, because usually it would be when you have a CH3 group or like an R group or an H group, those are not going to get ejected when that comes back down. It's going to be like your best leaving group in a way. And if there's not really any good leaving groups, then usually you don't do a Grignard reagent. It would just, if you had something else like that, it would probably just add on, force the oxygen up again, and then your oxygen would just get protonated. So you just have one more R group attached. Does that kind of make sense? So yeah, it wouldn't open up the ring though. That's the only thing. Good question. All right, so we're talking about, that was 14, 15 right below it. This is kind of going back to if I can change it into an acid halide, I'm going to, because it's very fast. So kind of think like that on the test. And I think A kind of gives you a good idea of what does that. Because once you can change it into an acid halide, you can pretty much do anything with it. And this is back to like, do you memorize all your reagents in a way? So let's go do 9. So we have like, we did start a little bit late, so I'm gonna stay after a little bit longer. Don't know if I want to stay in this room, but I'll be there. Between what's left is we have enols, we have electrophilic and nucleophilic aromatic substitution, we have free radical, we have oxidation reduction, we have spectroscopy. Is there any one that you particularly really want to do that you guys want to look at out of those, like 1, 2, 3, 4, 5? So like the last 5? You guys think about enols, then there's aromatics, then there's spectroscopy, then there's oxidation reduction and free radicals. Oxidation reduction? Everyone's good with that? Do you want to do that? Enols? So we got one for enols, one for oxidation reduction. Who wants to be the final person to decide? Anyone? Enols? All right, so I guess enols it is. So let's do enols. So that's just the next one. So let's look at number 2, which is right there. For enols, number 2, what do you guys think? Which sets of hydrogen atoms in this compound will undergo an exchange with these 2 reagents present? Somewhat unfamiliar in a way, right? So what do you guys think is going to happen here? It's basically testing which concept, what were enols and enolates chapter in? It was good, yeah, so alpha carbons. It's asking which one basically is very ready, most easily losing an alpha carbon. Does that make sense? So which one has the most conjugation with the alpha carbon in a way? So that'd be 2, that has an alpha carbon there. And then what's the other one that has an alpha carbon with hydrogens? So yeah, so 2 and 3, both are alpha carbons. So yeah, so that's just testing, do you know what an alpha carbon is type thing. So let's go look at a different one that covers a little bit more. So what about 19? So it's kind of like your synthesis. What do you guys think is going on here for 19? So you're starting with an anhydride, or malonic ester actually. OCH2. So you're starting with this one, right? Does that make sense? Do you guys remember this reaction? And this is a base. What is CH3O, so methoxy? Is that a base or an acid? So is this a base, right? Yeah, so between these two, if you see any reagent like this, pretty much ignore the Na or potassium, and then just realize that this is going to be negatively charged. So anytime you see an Na attached or potassium, just ignore that. So this is a really strong base, and it's going to deprotonate, right? But where is it going to deprotonate? So basically, which is my most acidic proton? Right, yeah, good. So alpha carbon and an alpha carbon. And in this case, that's what's going to happen. You're going to have our Br2 after deprotonates it. It's going to be an anion. And you're going to have your Br. So just like a general substitution reaction at that point. So it's going to add on to one side, and you have another CH3, basically another base, so it's going to take off the other proton. Does that kind of make sense with you guys? So now it's just going to add on to the other side of your CH2, Br. So if I were to draw that, it would be, so I'm going to O here, and then it would pretty much just add onto both. So these are the CH2 groups that were here. Does that kind of look familiar? All right, so that makes sense. If I added H3O plus and heat to this malonic ester synthesis, it would turn it into a carboxylic acid. Does that kind of make sense? And it would break it up and break up the molecule, and it wouldn't be like cyclic and stuff. So let's go to number 24. So this is another one. So how do you guys feel about 24? So basically, what is Cl2 and AOH going to do to this? And yeah, this one's a little weird of a reagent. The H3O plus at the end should give you a clue because it's protonating something that was previously negatively charged in the first step. So usually when we add H3O plus, it's like so far as we've seen, we've added to protonate an oxygen, right? And make sure that oxygen isn't still negatively charged. Between my answer choices, which one has an oxygen that has a hydrogen on it? Yeah, so it's either between B or D. The only thing with D though, or the only thing with B is that why would our oxygen add on to that carbon in a way? So yes, this one's a little interesting because like reagent-wise, have we seen this too many times before? Not really, because Cl2 is usually not just chilling there. So with 20, yeah, this is a haliform one. So yeah, this will add it on to, it'll change into a carboxylic acid. Does that kind of weirdly make sense? I think it's just like the H2O and the H plus kind of gives you a clue on what's going to form next. Now, I'm not sure if she'll test you guys on this, because was this in your chapters? This run, Cl2 and NaOH? Okay. That one's interesting. Okay, so our last group with enols and enolates, we could go to chapter 10, number 3, so the next one. I'll wrap it up. So let's do, so the next chapter, number 3, let's finish it up there. Looking at number 3, what do you guys think is going to be our answer? What's the problem with using this type of thing with a long chain carbon? You guys remember? So number 3 on electrophilic and nucleophilic aromatic substitution, what's the problem with using a long chain carbon with this one? Yep, exactly. So rearrangement's going to happen. It's not going to stay like A, and it's not going to be C, but because it doesn't rearrange to a tert butyl. But so, what do you guys think about B or D between those two? What's up? Oh, you want to see? Okay, so yeah. So let's just draw that one out. I think it's, so we have 4 carbons, 1, 2, 3, 4, 5, and we have our Cl. So once the Cl leaves, you're gonna have a positive charge on this, right? So 1, 2, 3, 4, you'll have a positive charge at the end, and that positive charge is gonna have like a hydrogen or hydride shift, and it's gonna go to a more stable position. So out of these positions, we have a primary and we have secondary, right? So it's gonna have a hydrogen, that one's gonna go over there, and then it's gonna go to my secondary position now. And then that's where it'll actually attach. Does that make sense? Good question. So that would, in this case, the only one that has it at the secondary would be B. So that one makes sense? So I think we should wrap it up, but I will be around, so we start a little bit late. So like, thank you for coming. I want to get like a quick head count on 4, 5, 6, 7, 8, 9, 10, 11, 12. But yeah, thank you guys for coming. Remember, like your ACS is multiple choice, so like answer like very strategically, and you can definitely cross a lot of stuff out, even if you don't like recognize it. All right, you guys got this. Good luck.
No problem.